Hello everyone, this is Nikhilian, Assistant Professor, Department of Civil Engineering, AJT Mangaluru. In our previous session, we had discussed about numericals on deflection of PSC members. In this session, we shall continue our discussion on numericals on deflection of prestressed concrete members. So let us consider the next example. A rectangular concrete beam of cross-section 150 mm wide and 300 mm deep is simply supported over a span of 8 meters and is prestressed by means of a symmetric parabolic cable at a distance of 70 mm from bottom of the beam at midspan and 125 mm from the top of a beam at support section. If the force in the cable is 350 kN and the modulus of elasticity of concrete is 38 kN per mm square, calculate the deflection at midspan when the beam is supporting its own weight, and second case is the concentrated load which must be applied at midspan to restore it to level of supports. So firstly, a rectangular concrete beam is having a parabolic cable, and the parabolic cable is having two eccentricities. So go through the question carefully. Here the eccentricity is at a distance of 75 mm from the bottom of a beam at the midspan. So here the overall depth of a beam is 300 mm. So y1 is equal to y2 is equal to 150 mm. That means the eccentricity will be 75 mm, that is E1 is equal to 75 mm. So we have taken eccentricity at midspan as E1 and eccentricity at the supports as E2 in the calculation or in the derivation of the formula. So E1 is 75, so 150 is Y2, so 150 minus 75 mm from the bottom, the remaining height it will be 75 mm, that is E1. And there is one more eccentricity at the supports. So it is given that 125 mm from top of a beam at the support section. So top of a beam, we are measuring the distance of a cable at the support at a distance of 125 mm from the top. So from the top means y1 is equal to 150 mm. So out of that 150 mm, the cable is at a distance of 120 mm from 125 mm from the top. Therefore, E2 is equal to 25 mm. So E2 is the eccentricity of a cable at the supports. It is 25 mm above the centroidal axis, and E1 is 75 mm below the centroidal axis. So it is also given that the pre-stressing force is 350 kilonewton. They have given Young's modulus of a concrete. Young's modulus of a concrete is 38 kilonewton per mm square. So we need to calculate what is the deflection at midspan when the beam is supporting its own weight. So when beam is supporting its own weight means we need to calculate what is the deflection of a beam at the midspan when the beam is having a deflection with respect to its own weight and with respect to pre-stress of a cable. So in first condition we are not going to consider live load for the calculation of deflection. And the second case, it is telling that the concentrated load which must be applied at midspan to restore it to the level of support. So in second case it is given that what should be the live load. So the live load is given a condition that the live load that has to be applied on a beam should be a concentrated load, and this concentrated load should be applied at midspan. So when this concentrated load is applied at the midspan of a beam, then the deflection should be 0. So what should be that concentrated load? So first let us consider what are the given data. So P is given pre-stressing force, it is 350 kilonewton. Moment of inertia, it is a rectangular beam by of cross section 150 by 300 mm. Therefore I is equal to BD cube by 12. This will be the final answer. Young's modulus of steel is given 38 kilonewton per mm square. E1 is 75, E2 is 25. So first let us calculate what is the deflection due to pre-stressing force. So it is a rectangular beam and the cable is having two eccentricities. So when the cable is having two eccentricities, the formula used for the calculation of deflection is PL square divided by 48 EI into minus 5 E1 plus E2. So you should be careful while considering this E1 and E2. So always remember that E1 is the eccentricity of midspan and E2 is the eccentricity at the supports. So if I substitute the values of P, L, E, I, E1 and E2 here, so I have substituted the values, the final answer is plus 12.7 mm. So plus is indicating upward. So upward means it is a deflection which is caused due to the compressive action of a pre-stressing member or pre-stressed cable. Now coming to the self weight of a beam. So we know the cross section of a beam, it is 150 by 300 mm. So cross section of a beam into density of concrete, we will get self weight of a beam. So cross section area of a beam is 0.15 meter into 0.3 meter into 24 kilonewton per meter cube. So 24 is nothing but it is the density of a concrete. So if density of a concrete is not given in the question, then we can assume density of concrete as 25 kilonewton per meter cube or 24 kilonewton per meter cube. So here we have considered the density of concrete as 24 kilonewton per meter cube. So area of a beam multiplied by density is equal to 1.08 kilonewton per meter. So this is the self weight of a PSC member. So in terms of kilonewton millimeter, this is equal to 0.00108 kilonewton per mm. So let us consider the first condition, deflection due to stress plus self weight. So deflection due to stress, that is deflection due to pre-stress, we have calculated here by using this equation, it is 12.7, and deflection due to self weight, we have an equation for this. So deflection due to self weight is equal to 4.5. So summation of this 12.7 and 4.5 gives us deflection due to pre-stress plus self weight. So 12.7 plus 4.5, which is equal to minus 8.2. So here minus is indicating the deflection is in upward direction, and here the plus is indicating, plus 4.5 is indicating the deflection is in downward direction. So it is negative because the deflection will be hogging shape, and here it is positive because the deflection will be having sagging shape. So net deflection is equal to minus 8.2 mm. So minus is indicating upward deflection. So that is the first condition. Second condition, we should calculate what should be the concentrated load that has to be applied at the midspan of a beam such that this deflection should be equal to 0. So the total deflection should be equal to 0. So that right now in the first condition the total deflection is minus 8.2. So if I want to make minus 8.2 mm to 0 means I should apply a point load at midspan in such a way that the deflection due to that point load should be equal to 8.2. Therefore this minus 0.2 and plus 8.2 will be equal to 0. So let us consider Q as a concentrated load which is required to obtain a deflection of plus 8.2 mm. So we have a deflection equation for a concentrated load or a point load, that is WL cube by 48 EI or QL cube by 48 EI. So here we have taken the symbol for concentrated load as Q, therefore it is QL cube by 48 EI. So as I told you, the deflection due to this value should be equal to plus 8.2. Then only the net deflection will be equal to 0. So we know the value of L, we know 48, we know what is EI. Then only the unknown is Q. So Q is equal to, by rearranging the terms, you will get 9.9 kilonewton. So if I apply a concentrated load of 9.9 kilonewton at the midspan of a beam, then the total deflection will be equal to 0. So these are the two conditions which are asked in the question. Now let us consider next example. So a simply supported beam with a uniform cross section spanning over 6 meters is post tensioned by two cables, both of which have an eccentricity of 100 mm below the centroid of a section at midspan. The first cable is parabolic and is anchored at an eccentricity of 100 mm above the centroid at each end. The second cable is straight and is parallel to line joining the support. The cross-sectional area of each cable is 100 mm square and they carry an initial stress of 1200 Newton per mm square. The concrete has a cross-section of 2 into 10 to the power 4 mm square and a radius of gyration of 120 mm. The beam supports two concentrated loads of 20 kN each at the third point of a span. EC, Young's modulus of concrete, is 38 kN per mm square. Calculate using Lenz's simplified method. First one, the instantaneous deflection at the center of a span, and the second one, the deflection at the center of a span after 2 years, assuming 20% loss in pre-stress and the effective modulus of elasticity to be one third of short-term modulus of elasticity. In this problem, a rectangular beam is provided with two cables. So the first cable is a parabolic cable, and the parabolic cable is having an eccentricity of 100 mm below the centroid at midspan, and the same parabolic cable is having an eccentricity of 100 mm above the centroid at both the ends. And the second cable is a straight cable, and the straight cable is having an eccentricity of 100 mm below the centroidal axis, and it is also given parallel to line joining the support. That means it is a straight cable, it is having a constant eccentricity. So the cross section area of each cable is 100 mm square and each cable is carrying an initial stress of 1200 Newton per mm square. So the cross section area of concrete beam is given, radius of gyration is given, and the beam is supporting two point loads of 20 kN each at a distance of one third of a span. So Young's modulus is given, that is EC is equal to 38 kN per millimeter square. So what we need to calculate? In the first case we need to calculate what is the instantaneous deflection at center of the span, and the second case is deflection at center of the span after 2 years. So instantaneous deflection means we are going to calculate the deflection of a beam or a member within a short time or at a time of construction or at a time of loading. And in the second case, we need to calculate the deflection of a beam after 2 years of construction. So after 2 years means obviously there will be some losses of pre-stress. So here it is given that we should assume the loss of pre-stress as 20%, and the Young's modulus of a steel is one third of a short-term modulus of elasticity. So we have two cables, one is a straight cable and one is parabolic cable. So the procedure is same as previous problem. So we need to calculate the deflection due to self weight, we should calculate the deflection due to live load, and we should calculate the deflection due to pre-stress of a cable. So the equations are same for the calculation of deflection due to self weight and calculation of deflection due to live load. Whereas to calculate the deflection due to prestressed cable, we have different equations depending upon the cable profile. So here we have two cable profiles, one is parabolic and one is linear or straight cable. So we need to calculate a deflection due to pre-stress for both the cases. So let us see that later. So first we know the equations for calculating the deflection due to live load, deflection due to dead load, and deflection due to pre-stress of straight cable and parabolic cable. So in that equations we have A, we have I, we have P, and we have E1 and we have E2. So first let us calculate all this data. So firstly it is given that cross section area is 2 into 10 to the power 4 mm square. Moment of inertia, so radius of gyration is given. So moment of inertia is equal to A I square, because radius of gyration is equal to square root of square root of A by I. So I is equal to AI square, that is equal to 288 into 10 to the power of 6 mm square. P is given, P naught is given, that is each cable is carrying an initial stress of 1200 Newton per mm square. So pre-stressing force is equal to area into initial pre-stress. So area is 2 and 2 into 10 to the power of 4 multiplied by 1200. We will get P, that is initial pre-stressing force. So initial pre-stressing force is 120 kilonewton. L is span, it is 6 meters. In millimeters it is 6000 millimeters. So self weight is equal to 0.0048 kilonewton per mm. So self weight means we know cross section area of a member is 2 into 10 to the power of 4. We know the density of concrete is 24 kilonewton per meter cube. So cross section area multiplied by density of concrete, we will get self weight of a beam is equal to 0.0048 kilonewton per mm. Now concentrated loads at third point of a span. So it is given that two point loads are acting at an distance of one third of a span. So the intensity of point load is 20 kilonewton. So what is the downward deflection due to self weight of a beam? So self weight of a beam is 0.0048 kilonewton per mm. So we know what is the formula. The formula is 5 WL to the power 4 divided by 384 EI. So 5 into W, we have taken it as self weight as G. So into self weight into L to the power 4, it is 6384 into E into I. So that gives us 0.74 millimeter. So 0.74 millimeter is the deflection due to self weight of a beam. So it is plus 0.74 mm. That indicates that the deflection is in downward direction. Now, what is the downward deflection due to concentrated loads? So live load is in the form of 2-point loads. Therefore, to calculate the deflection due to 2-point loads, we have equation 23QL cube divided by 648 EI or 23 WL cube divided by 648 by 648 EI. So we know what is the intensity of point load. So the intensity of point load is 20 kilonewton. So L is 6 meters. In millimeters it is 6000 millimeters. 648 into 38 into 288 into 10 to the power of 6. So EI is the rigidity modulus, where this is Young's modulus of concrete, and I is moment of inertia of a member. Therefore, the deflection due to live load is equal to 14.10 mm. So 14.10 mm is a positive deflection, or it is a deflection which is having sagging in nature. That is, the deflection is in downward direction. And now let us calculate the deflection due to pre-stressing force. So as I told you, we have two cables, and out of two cables, one cable is parabolic cable and other cable is straight cable. So we need to calculate the deflection due to both the cables. First, let us consider deflection due to parabolic cable. So it is a parabolic cable which is having two eccentricities. One eccentricity at the midspan, that is E1, and the second eccentricity is at the supports, and that eccentricity is E2. So E1 is the midspan eccentricity, E2 is the support eccentricity. So this is the equation we have for a parabolic cable with two different eccentricities. So substitute the values. P is 120, that is pre-stressing force in each cable. L is the span, 48, and 38 288 into 10 to the power of 6 is modulus of rigidity minus 5 into E1 is 100, which is eccentricity at the midspan below the centroidal axis, plus E2 is 100, which is eccentricity at the supports above the centroidal axis. So this gives minus 3.27 mm. So here the minus sign is indicating that the deflection is in upward direction. So always remember that the deflection due to pre-stressing force is always in upward direction, because after anchoring the cables, the cable or a tendon will try to regain its original shape and size. So during this process, what will happen? The member will undergo a hogging shape, or it will undergo a concave shape. Hence, the top fibers will be under tension and bottom fibers will be under compression. So deflection due to straight cable. So in previous step we have calculated deflection due to parabolic cable, and now we shall calculate the deflection due to straight cable. So deflection due to straight cable is PE L square by 8 EI. So this minus is indicating the cable is having a deflection in upward direction. So P is the pre-stressing force in straight cable. So pre-stressing force in a straight cable is 120 kilonewton. E is 100. Span is 6 meters. So 8 into EI, Young's modulus of concrete and moment of inertia, that gives minus 4.92 mm. So again I am telling you the minus sign is indicating upward deflection. So what are the instantaneous deflection due to pre-stress of cable, due to self-weight of a member and live load acting on a member? That is minus 3.27. This minus 3.27 is the deflection due to parabolic cable. minus 4.92, this is the deflection due to straight cable, plus 0.74 plus 14.10, which is equal to 6.67 mm. So again it is plus 6.65 mm. So plus sign is indicating that the deflection is in downward direction. So this is the first condition. So in the second condition, he has asked us to calculate what will be the total loss in the member after 2 years, and he has given that the Young's modulus will be equal to one third of a Young's modulus during the transfer. So this is the condition. This is the condition. Young's modulus after 2 years is equal to one third into E, that is E by 3. So one third of the Young's modulus at the time of transfer, and the loss of prestress is 20%. So to calculate the deflection due to prestress, so upward deflection, so here I have considered it directly. So upward deflection means it is the deflection due to prestress of a cable. So here you can see, so this formula is deflection due to straight cable, and this one is due to parabolic cable. So we can consider from the beginning and we can calculate the deflections for the value of E by 3. So it will be a time consuming process, so that what we can do is we can directly calculate the deflection of a member after 2 years by considering the given condition. So here what happens, here we have E, so E is equal to 1 by 3. So if 1 by 3, I will just cross multiply this. So I will transfer 3 towards here, and 0.8 is the loss ratio, 0.8 into 3.27 plus 4.92. So 3.27 is the deflection due to parabolic cable, and 4.92 is the deflection due to straight cable. So here, when the stress is 100%, then the deflection will be 3.27 and 4.92. When the stress is 80%, when the amount of stress in the cable is 80%, that is after 2 years, what will be the deflection? So 80% into 3.27 plus 9.2 multiplied by 3. So 3 is this one. Young's modulus of concrete after 2 years is equal to 1 by 3 times of that of during the transfer. So Young's modulus will be equal to 3 times the Young's modulus of that of transfer. So 3 into 0.8 into transfer of 3 into 0.8 into deflection due to prestress of a tendon, that equal to 19.65 millimeter. So downward deflection. So downward deflection, again we have this equation, so everything is same in downward deflection. So only the change is E. Young's modulus is 3 times the Young's modulus of that of during the transfer. So again 3 into 0.74 plus 14.10, that equal to 44.52 mm. So 0.74 is the deflection due to self weight, 14.10 is the deflection due to live load. So this both deflection are in downward direction. So total downward deflection is equal to 3 Young's modulus into total deflection, that gives 44.52 millimeter. Then net downward deflection or net deflection equal to 44.52 minus 19.65. So I am writing here minus because it is a upward deflection. It is upward deflection, hence I am considering it as minus. So total deflection or net deflection is equal to plus 24.87 millimeter. So plus 24.87 millimeter means the deflection is in downward direction. Now let us consider one more example. So a prestressed concrete beam having a cross-sectional area A of 5 into 10 to the power of 4 mm square is simply supported over a span of 10 meter. It supports a UDL of 3 kilonewton meter 3 kilonewton per meter as an imposed load, half of which is non-permanent. The tendon follows a trapezoidal profile with an eccentricity of 100 mm within middle third of the span and varies linearly from third span point to 0 at the support. The area of tendon is equal to 350 mm square, having effective stress pre-stress of 1290 Newton per mm square immediately after transfer. So using the following data, calculate the short-term deflection and long-term deflection. So these are the given data. So moment of inertia is given, Young's modulus of concrete is given, area is given, Young's modulus of steel is given, density of concrete is given, creep coefficient of concrete is given, shrinkage is given, and relaxation of steel is given. So we should calculate the short-term deflection as well as long-term deflection. So I think you remember what I said in previous session. So in previous session, I said to you that long-term deflection can be calculated in two ways. So we have two equations to calculate the long-term deflection. So the first formula can be used when these values are given. That is when we find out the losses due to different parameters due to creep, due to shrinkage, and due to relaxation of steel. Then we are going to use first formula. So in this problem, let us use that first formula. So what is given in the question? So a rectangular beam with an area of 5 into 10 to the power of 4 mm square is having a span of 10 meter. It is a simply supported beam with a span of 10 meter and it is supporting a UDL of 3 kilonewton per meter. So this UDL is a live load. So the intensity of live load acting on a beam is 3 kilonewton per meter. And he has given a condition, half of which is non-permanent. So out of this 3 kilonewton per meter, 50%, that is half of the load is non-permanent load. That means out of this 3 kilonewton per meter, only 1.5 kilonewton per meter will be the live load. That is only non-permanent load, and remaining 1.5 kilonewton per meter will be as a dead load in the form of dead load. So the best example for this is if we consider a classroom. So while designing what we will do, we will design the classroom by considering 60 students. And for that 60 students, we will consider the weight of benches and desks. So when the student leaves the classroom, then the that live load, that movable load, which is in the form of benches and desks, will act as a dead load because throughout the year that benches and that desks will be within that classroom only. Hence it is similar to that one. So out of 3 kilonewton per meter, 50% of the load is non-permanent. 50% of the load will be like a live load and remaining 50% of a load will act as a dead load. So the tendon follows a trapezoidal profile with an eccentricity of 100 mm within the middle third of a span and linearly varying the third span points to 0 at the support. So area of tendons is given, it is 350 mm square, and effective pre-stress which is applied to the tendon is 1290 Newton per mm square. So a rectangular beam and trapezoidal cable profile means it is like this. So this is the given condition in a beam. So it is linear up to from middle span to one third of the distance, and one third of the distance is linearly varying, and at the eccentricity it is 0 on either side. The eccentricity is 0 at the supports and either side, and it is given that the eccentricity of a cable at mid span is 100 mm. So this eccentricity at the mid span is 100 mm. So up to this one third distance from here, from the support up to one third distance, the eccentricity is 100 on either side, and from this one third distance the eccentricity is linearly varying to 0 with respect to the supports. So here also the procedure is same. So deflection due to pre-stressing force. So referring to the figure, substituting the values of L1 and L2. So as I told you, L1 is from year to year, where the direction of cable changes, that is L1, and L2 is from year to mid span, it is L2. So in the question it is given that trapezoidal profile with an eccentricity of 100 mm within the middle third of the span and varies linearly from third span point to 0. That means the distance from year to year is 1 by 3. 1 by 3. So 1 by 3 means it is L into 1 by 3, one third of the span. Therefore L1 is equal to 33.33 meter, and L2, so the span of a beam is given, the span of a beam is 10 meter. So mid span is 5 meter. Out of this, from here to here it is 5 meter. In that 5 meter, L1 is 3.33, that is L by 3, because the cable has changed its direction at a distance of one third from the support. So L1 is 3.33 and L2 is 5 minus 3.33. Therefore L2 is equal to 1.66 meter, and eccentricity E is equal to 100 mm. Therefore deflection due to pre-stressing force is equal to substituting the obtained values in the equation. So we know what is P, it is given. We know eccentricity, it is 100. The values of E and I is given. L1, L2 is known. So substituting the values of each term in the formula, we will get deflection due to pre-stressing force is equal to minus 31 millimeter. So minus is indicating the deflection is in upward direction. Now deflection due to non-permanent load. So non-permanent load is nothing but it is a live load. So in the question it is given that a imposed load of 3 kilonewton per meter. But again he has given a condition, out of that only 50% will act as a live load. That means then the remaining 50% will be in the form of dead load. So deflection due to non-permanent load or live load. So 50% is the live load. Therefore Q is equal to 1.5 kilonewton per meter. Here 1.5 kilonewton per meter is the 50% of given live load. So we know that deflection due to UDL is 5QL to the power 4 divided by 384 EI. So substitute the values in this equation. You will get the deflection due to live load or deflection due to non-permanent load, that is 12.8 mm is the deflection due to live load, and this deflection is acting in downward direction. And deflection due to permanent load or sustained load. So permanent load or sustained load is nothing but it is a dead load. So it's the deflection due to dead load. So let us assume density of concrete as 24 kilonewton per meter cube, and here the cross section area of a beam is given, it is 5 into 10 to the power of 4 mm square. Therefore area into density of a concrete will get self weight of a member. So the self weight of a member will be around 1.12. So around 1.12 will be the self weight, and plus we need to add the 50% of the live load. See here, out of 3 kilonewton meter, only half of the load is a non-permanent load. Then the remaining half will be in the form of permanent load. Therefore, self weight of a beam will be self weight of a beam plus 50% of the imposed load. That will be the total self weight of a member. So that will be equal to 2.68 kilonewton per meter. So self weight is equal to 2.68 kilonewton per meter. So it is in the form of UDL. Therefore we have a formula 5 into WL to the power 4 by 384 EI. So here W is considered as G. So substitute the values of G, L, E and I. We will get what is the deflection due to self weight of a beam. So deflection due to self weight of a beam is 22.8 millimeter, and this deflection is in downward direction. Now short term deflection. So as I said you, short term deflection means it is the deflection due to self weight, due to live load and due to pre-stress of a cable. So in short term deflection we shall consider two cases. When non-permanent load is acting, the short term deflection is minus 31 plus 12.8 plus 22.8. So non-permanent load, in the first case we are considering the short-term deflection along with the live load. So we have considered the live load for calculation of short-term deflection. So when we consider the live load, the short-term deflection will be 4.6. So minus 31, it is the deflection due to pre-stressed cable, plus 12.8 is the deflection due to it is the deflection due to live load. Then 22.8 mm is the deflection due to self weight of a member. Therefore total deflection is equal to 4.6 mm. So it is downward because minus 31 plus 12.8 plus 22.8 is equal to 4.6 mm, and the deflection is acting in downward direction. The second case is when the non-permanent load is not acting, the short-term deflection is minus 31 plus 22.8, that is equal to minus 8.2 mm. So here we have not taken the deflection of live load into consideration. So without taking the deflection of live load into consideration, the deflection of a member is equal to minus 31. This is the deflection due to pre-stress, and plus 22.8. This is the deflection due to self weight of a member, that is equal to minus 8.2 mm. So here the negative sign is indicating that the deflection is in upward direction. Now coming to the long-term deflection. Here, long-term deflection means we are going to consider the deflection by considering all the losses, because they have given the values for loss due to creep, loss due to shrinkage, and loss due to relaxation. Hence, we shall consider long-term deflection by considering all the losses of prestress. So we know to calculate what is the losses of prestress. So the losses of prestress is due to creep of concrete, shrinkage of concrete, relaxation of steel, and friction of cables. So here, if we want to calculate the losses in concrete, we need to know what's the compressive stresses developed in the concrete. So compressive stresses developed in the concrete, Fc is equal to F or P by A, initial pre-stressing force divided by A, that is area, plus initial pre-stressing force into E square by moment of inertia. So E square is 100 into 100. So E square, here we have two eccentricities, so 100 into 100, which gives Fc is equal to 90 Newton per mm square. So modular ratio is equal to ES by EC. The values of Young's modulus of steel and Young's modulus of concrete is given. It is 234. So the ratio of this is equal to 5.88. And now let us consider the different types of losses in prestress. So first let us consider a loss of prestress due to relaxation. So it is given that loss of prestress due to relaxation is 10% of initial prestress. So 10% of initial prestress means we will get the loss as 129 Newton per mm square. So loss due to shrinkage. So loss due to shrinkage is equal to 450 into 10 to the power of minus 6 into 200 into 10 to the power of 3. So 450 into 10 to the power of minus 6 is nothing but it is shrinkage coefficient, which is given in the question, and this 200 into 10 to the power of 3 is Young's modulus of steel. Therefore, the loss due to shrinkage is equal to 90 Newton per mm square. So loss due to creep. So we know that the loss due to creep formula is CMFC, where C is creep coefficient, M is modular ratio, F is compressive stresses in concrete. So substituting the value of C, M and Fc, we will get loss due to creep is equal to 223 Newton per mm square. Therefore, total losses in pre-stress is equal to 442 Newton per mm square. So it is given that P is equal to 4,51,500 Newton. So P is the initial pre-stressing force, that is 4,51,500 Newton. So this we have calculating by using area and stresses developed in the steel. So delta P is the loss of pre-stressing force. So what's the loss of pre-stressing force? That is 442 into area of the cable. So 442 is the total losses of pre-stress. So total losses of pre-stress multiplied by cross-section area of a cable, we will get loss of pre-stressing force, that is delta P. So we will get what will be the loss of applied force. So that is 1,54,700 Newton. So what is the final pre-stressing force that is available in the cable? So final pre-stressing force available in the cable is initial pre-stressing force minus the pre-stressing force which has lost due to all these parameters, that is 1,54,700. Therefore, the effective pre-stressing force or final pre-stressing force which is available in the cable is equal to 2,96,800 Newton. Now, if I consider the average of pre-stressing force, so if I consider the average means I will consider initial pre-stressing force plus final pre-stressing force divided by 2. Therefore, the average of pre-stressing force will be 3,74,150 Newton. Now let me calculate long-term deflection only due to pre-stress. So here, in this case, I am not going to consider the deflection due to load. So I hope you remember what is the first formula to calculate long-term deflection, which was said in previous session. So in the same formula I am using here, but the formula is being splitted into two parts. That is, in the first part I have considered only deflection due to pre-stress, and in the second part I have considered deflection due to permanent load, that is due to self weight. So it's the deflection due to pre-stress, that is long-term deflection due to pre-stress. So deflection due to initial pre-stressing force minus deflection due to loss of pre-stressing force plus deflection due to average pre-stressing force due to creep with phi is equal to 2. So creep coefficient is given, that is 2. So we have calculated what is the deflection due to initial pre-stressing force. So that is 31. 31 is the deflection due to initial pre-stressing force we have calculated in first step here. So in the first step itself we have calculated deflection due to pre-stressing force, that is 31 mm. Then deflection due to loss of pre-stressing force. So for initial pre-stressing force is the deflection, then what will be the deflection that may occur due to loss of pre-stressing force? So we know that here we have calculated what is the loss of pre-stressing force. So here for initial pre-stressing force of 4,51,500, the deflection is 31 mm. Then what will be the deflection for loss, that is 1,54,700. Then plus a deflection due to average pre-stressing force plus, so for the initial pre-stressing force of 4,51,500, the deflection is 31. Then what will be the deflection for average pre-stressing force of 3,74,150 Newton per mm square into 2, that is due to creep coefficient 2. So multiplied by 2, we will get 31 minus 10.6 plus 51.4 is equal to 72 mm. So here plus is indicating upward direction. So I am coming to the second part of that equation. So long-term deflection due to permanent load, 1 plus 5 into short-term deflection. So 1 plus 5, it is creep coefficient 2, short-term deflection is 22.8, where we have already calculated short-term deflection, it is 22.8, which is equal to 68.4 mm. So 68.4 mm, it is a downward deflection. So downward deflection because it is a deflection due to permanent load. So permanent load means it is a dead load. So the dead load will always be acting in downward direction, hence the deflection will be in downward direction. Now coming to the same equation, and here the long-term deflection is considered due to live load. So what's the deflection due to live load? So here we have calculated the deflection due to live load. Deflection due to live load is 12.8 mm. So deflection due to live load is 12.8 mm and it is downward direction. So total long-term deflection is computed as when non-permanent load is acting. So when we consider live load active on a beam, then what will be the deflection for long time? That is 7 minus 72. So minus 72 is deflection due to pre-stress. Then 68.4, that is long-term deflection due to dead load. then plus 12.8 long-term deflection due to live load. So that will be 9.2 mm in downward direction. So when I consider the live load acting on a beam, then the deflection of a beam will be 9.2 mm, and this deflection is long-term deflection. And when I consider the deflection of beam without taking live load into consideration, then the deflection will be minus 72. This is the long-term deflection due to prestress plus 68.4. So 68.4 is the long-term deflection due to dead load or self weight of a member. Therefore, the total deflection is equal to 3.6 mm. So it is in upward direction. So now let us move on to the requirement of various codes of practice. So as I told you in the beginning of this deflection discussion, the deflection of a member should be within permissible limit as per IS provision. So what is the provision given for the deflection by Indian standard practice? So the total deflection below the level of supports should be between span by 200 to span by 300. Deflection that occurs after adding of partitions should be between span by 500 to span by 1000. So in general we can tell that the deflection in upward direction should be less than span by 300 mm, and a deflection in downward direction should be less than span by 250. So these are the permissible limits as per IS codal provision. So let us consider an example. So a concrete beam with a symmetrical I section as flange width and depth 200 mm and 60 mm respectively. The thickness of web is 80 mm and overall depth is 400 mm. The beam is pre-stressed by a cable carrying a force of 1000 kN. The span of beam is 8 meter. The center line of a cable is 150 mm from soffit of a beam at the center of a span, linearly varying to 250 mm at the support. So compute the initial deflection at midspan due to pre-stress and self-weight of a beam, assuming EC Young's modulus of concrete is equal to 38 kN per mm square. Compare the deflection with limiting deflection permitted in IS 1343. Take density of concrete is equal to 24 kN per. In this problem, it is a symmetrical high section beam and cross section area of flanges and web is given. So here we need to calculate what is the deflection due to pre-stress and self weight of a beam, and we should check that whether the deflection is within permissible limit as specified by IS 1343. So we know the formulas to calculate a deflections due to pre-stress and a deflection due to self weight. So the data is required to substitute in the formulas are: we need moment of inertia, we need self weight of a beam, we need cross section area, and we need what is Young's modulus of concrete. So firstly, I will calculate self weight of a beam. So self weight of a beam is equal to 1.12 kilonewton per meter. So self weight of a beam is obtained from cross section area into density of concrete. So cross section area of a I section is equal to 2 into area of a flange, that is 2 into 200 by 60 plus cross section area of a web. So the cross section area of a web is 80 into 400 minus 60 plus 60. Therefore cross section area of a web will be 80 into 80 into 280. That will be the cross section area of a web. So the total area of I section will be 2 into 200 by 60 plus 80 into 280, this multiplied by 24, we will get self weight of a concrete, that is 1.12 kilonewton per meter. So in terms of kilonewton per millimeter, it is 0.00112 kilonewton per millimeter. So pre-stressing force is given, it is 1000 kilonewton. So the beam is pre-stressed by cable carrying a force of 1000 kilonewton. It is given, that is P is equal to 1000 kilonewton. Moment of inertia. So it is a I section. So first I will consider I section as a rectangular section. So I will take it as capital BD cube by 12 minus, in that whole rectangular circle I will deduct two rectangular circles on either side. So I will get a moment of inertia is equal to 847 into 10 to the power of 6 millimeter to the power 4. So E1 is 50 mm. So it is given that the cable is 150 mm from the soffit of a beam at the center of a span. So the overall depth of a beam is 400 mm and it is a symmetrical beam. Therefore, y1 is equal to y2 is equal to 200 mm. That is, the centroidal axis lies at a distance of 200 mm from top flange as well as from the bottom flange. So the cable is having an eccentricity of 150 mm. Sorry, the cable is placed at a distance of 150 mm from the soffit. That means the distance from the centroidal axis to the bottom fiber, or the distance from CG to soffit, is 200 mm and the cable is placed at 150 mm from the soffit, and therefore the cable is having an eccentricity of 50 mm below the centroidal axis, and the cable linearly varying to 250 mm at the support with respect to the soffit. So 250 mm with respect to soffit means E2 will be 50 mm, that is plus 50 mm, because E2 will be above the centroidal axis. So centroidal axis is lying at a distance of 200 mm. So if the cable is above, or so if the cable is at a distance of 250 mm from the soffit, means the cable is having an eccentricity of 50 mm above the centroidal axis and the span is 8000 millimeter. So substituting these values in the formula to calculate the deflection due to self weight. So the formula is 5WL to the power 4 divided by 384 EI. So here W is taken as G, therefore 5 into self weight into span divided by 384 EI. Hence modulus of concrete is given 38 and moment of inertia we have calculated, it is 847 into 10 to the power of 6. Therefore deflection due to self weight is equal to 1.86 millimeter. So the plus sign indicates the deflection is in downward direction. And now self weight due to pre-stressing force. So the cable is having two eccentricities and the cable is linearly varying cable. So for this cable we have this equation to calculate the deflection due to pre-stressing force. So substituting the values of P, E2, L2, E1, E2 and EI, we will get deflection due to pre-stressing force is equal to minus 4.1 millimeter. So here the minus sign is indicating that the the deflection due to pre-stress is in upward direction. Therefore, deflection due to pre-stress plus self-weight. Deflection due to pre-stress is minus 4.1 plus deflection due to self-weight is plus 1.86. So the total deflection is minus 2.24. So again, the deflection is in upward direction. So what is the permissible deflection according to IS 1343 for upward deflection? So it is span by 300. So span is 8000 by 300, which gives 26.6 millimeter in upward direction. So the deflection is 2.24. It is the deflection of maximum deflection of a beam, and allowable deflection of a beam as per IS 1343 is 26.6 mm. Therefore, the actual deflection is within permissible limits. Now let us consider one more example. A pre-stressed concrete beam of rectangular section 120 mm wide and 300 mm deep, spans over 6 meters. The beam is pre-stressed by a straight cable carrying an effective force of 180 kN at an eccentricity of 500 mm. If it supports an imposed load of 4 kN per meter and modulus of elasticity of concrete is 38 kN per mm square, compute the deflection at the following stages and check whether they compile with IS code specification. So first case, upward deflection under pre-stress plus self-weight, and the second case is final downward deflection under pre-stress plus self-weight plus imposed load including the effect of creep and shrinkage. Assume creep coefficient to be 1.80. So here this first condition is same what was there in previous problem. So the second condition is we are going to calculate the deflection with respect to pre-stress, self-weight and live load. So the live load is given, the live load is 4 kN per meter. So it is a rectangular section of 1 by 120 by 300 mm cross section. So the force is 180 kilonewton. So eccentricity is 50 mm and moment of inertia 27 into 10 to the power of 7 mm square. So BD cube by, it is a rectangular section, therefore moment of inertia is equal to BD cube by 12. So L, it is 6 meters. So self weight. So self weight is calculated by using the equation cross section area, that is 120 into 300 into density of concrete. So that gives 0.86 Newton per mm. So either you can keep this in terms of kilonewton per meter, kilonewton per millimeter, Newton per meter, Newton per millimeter. So here the self weight area into density gives 0.86 into Newton per mm. So imposed load is given and Young's modulus of concrete is given. So these are the data given in the question. So here please make a note that the eccentricity is not 500 mm. The eccentricity is 50 mm below the centroidal axis. So here there is a mistake. It is been entered as typed as 500. So it is 50 mm. Now let us calculate the deflection due to pre-stressing force. So deflection due to pre-stressing force is PEL square by 8EI. So substituting the values of PEL and EI, we will get the deflection is equal to 4 millimeter and the deflection is in upward direction. So the deflection due to pre-stressing force is 4 millimeter. So deflection due to self weight of a beam. So self weight is always a UDL. Therefore, deflection due to self weight of a beam is equal to 1.4 millimeter by using this equation. So deflection due to self weight and live load. So the total deflection due to self weight and live load is equal to 5 into G plus Q into L to the power 4 by 384 EI. Here G will be the dead load and L will be the live load. So the deflection due to self weight and live load is equal to 8 millimeter. So this deflection will be in downward direction as live load and dead load will always be acting in downward direction. So when we calculate the deflection due to self weight and live load, then we can skip this step. That is, we can skip the calculation of deflection due to self weight. And now coming to the first condition, deflection due to pre-stress plus self weight. So what's the deflection due to pre-stress plus self weight? It is minus 4 plus 1.4. So the total deflection is minus 2.6. So minus sign indicates that the deflection is in upward direction. So for upward direction, the permissible limit is span by 300. So span is 6000 by 300. We will get 20 mm. So the maximum deflection occurring in a beam is 22.6 mm and permissible limit is 20 mm. Hence, the upward deflection is within permissible limits. So the second case is deflection due to pre-stress self weight plus live load. So to calculate the deflection due to this, we should include effect of creep and shrinkage. So we know what's the deflection due to pre-stress, it is -4. Deflection due to self-weight and live load, we have calculated here. We have calculated the deflection due to self-weight and live load by considering both the loads in a same equation or in the same step. So that is 8, and including the effect of creep, that means 1 plus 5. It is including the effect of creep is equal to 4.0 into 1 plus 1.8. So the value of creep is given. If the value of creep is not given, we should assume the value of creep as between 1.5 to 2. Therefore, the deflection due to pre-stress plus self-weight plus live load, including the effect of creep and shrinkage, is equal to 11.2 millimeter. So permissible limit for downward deflection as per IS 1343 is equal to span by 250. So span is 6000 by 250, which gives 24 millimeter. So the maximum deflection occurring in a beam is 11.2 millimeter, and the permissible limit is 24 millimeter. Therefore, the deflection in downward direction is within permissible limit. So this is an assignment question. So try to solve this question and submit the assignment by 5 o'clock. So in all these problems of deflection, there is no much difficulty. Only the thing you should remember is you should remember the formulas depending upon the cable profile to calculate the deflection due to pre-stressing force, and the formulas to calculate the deflection due to self-weight and dead load is almost same. Either the self-weight will be UDL or it will be, so the self-weight will be UDL and live load will be either UTL or point load. So the thing is, you should remember the formulas to calculate deflection due to pre-stressing force. So if it is difficult to remember this formula, then remember one thing: deflection is equal to, so like this. So you can calculate the deflection of this beam by taking the moment of 50% area of a BMD about the support. So if I take the moment of this area and this area about the support, then I will get deflection due to pre-stress.